The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome everyone to our latest webinar, Taking the Guesswork Out of Designing and Deploying Small Cell Networks, presented by iBwave and Airvana. If you design small cell networks, then you are well aware that issues like dropped calls and throughput can cause some major headaches after deployment. In this webinar, you will learn through concrete examples and a real-life case study about the best practices of designing and deploying small cell networks right from the start to save you from future issues. First of all, I would like to introduce our speakers today. From iBwave, we have Marc-Antoine Lamontagne. Marc-Antoine is the Senior Product Manager for iBwave Design with more than 15 years of experience in the telecom industry and over 5 years of direct in-building experience. He is responsible for the overall product strategy and roadmap of the product, and he regularly meets with wireless operators, system integrators, and equipment manufacturers around the world from the in-building industry. He also participates in various industry events. Marc-Antoine holds a bachelor's degree in engineering and a postgraduate diploma in business administration. From Airvana, we have Josh Adelson. Josh is the Director of Product Marketing at Airvana. He is responsible for marketing Airvana's award-winning OneCell C-RAN small cell solution. He has over 20 years experience in mobile communications, content delivery, and enterprise networking. Prior to joining Airvana, Josh has held product marketing and management positions with Peer App Brooktrout Technology and Motorola. He holds an MBA from MIT Sloan School of Management and a BA from Brown University. Now, before we begin, I would just like to mention a few housekeeping items. You will receive slides and video recording of this webinar by email within the next few days. Also, if you have any questions during the webinar, please type them in the GoToWebinar box, and we will get to those questions within the last 15 minutes of our webinar. So for today's agenda, we have really focused on two main things. First of all, Marc-Antoine will discuss the best practices to ensure successful deployments, focusing on small cell networks. And then Josh Adelson will take us through the case study of modeling C-RAN small solution user experience with the help of iBwave. Now, without further ado, I'll ask Marc-Antoine to start the presentation. Thank you.
Thank you, Amna. So just before we start, we'll give a few words about iBwave for people who may not be familiar with the company. iBwave is a software provider for the in-building network market. The company was created 12 years ago, and it created a software called iBwave Design for RF engineers to design in-building systems, and over time it has complete portfolio of products, adding mobile solution, cloud-based solutions, and specialized training on in-building. Products from iBwave are used by over 700 customers around the world in more than 87 countries. So we are very pleased to have this webinar with Airvana. We've done webinars in the past on stadium deployments, but most of them has been done with active DAS solution, and in this case we have a deployment of a stadium using a small cell solution. So it's very nice to see that the technology is evolving to support that kind of venue with small cells solution. So just before we get to the case study, I will go over a couple of best practices to ensure that your deployment will be successful So the best practices for designing your solutions for LTE and small cells in particular. So we're going to cover concept of capturing user requirements, modeling the venue in its environment, how to consider the impact of the macro network, and the use case of small cells specifically in your design. So the first thing that is important to take into account as you prepare for your small cell design is to capture user requirements. It's important to understand the type of applications that will be used throughout the venue. So obviously you would have very different needs if you're located in a stadium, an hotel, or an office building. The requirements of data throughput and the type of application that will run on your network may be completely different. So it's important to capture that and understand that as you plan your design to make sure that your network will meet the need of your customers. The second aspect to consider are the technologies that needs to be supported by your network. Different customers may have completely different needs. Some may have an existing Wi-Fi network, for example, for data, and they just want to add voice coverage for cellular, let's say on 3G and 4G. Some others may not have an existing network, and they would prefer to have a full data plus voice network running on LTE. So again, depending on the technologies that are required by the customer, you may have a different design to be done. And lastly, another aspect that needs to be considered as you plan your design is to understand the ingress and egress of people entering and leaving the building. So those locations that are identified in the diagram on the right are the location where the user will be doing handoff from and to the macro network to the in-building system. So those zones are important to consider to make sure that you don't have drop calls in those locations. The other aspect that is very important is to model your building in its environment. So so if you take a building just like you have on the picture, around the building you will have obviously a macro network that will generate some signal and will generate interference inside the building. So that interference will impact the quality of the network that you're putting in place. So that's very important to take into account. In some urban area, you might have also some outdoor small cells that are deployed in the street in front of the building. So those could be also contributing to the level of noise that you have around the building and affecting the design or the network that you're putting in place. And lastly, you might also have surrounding buildings that have their own in-building solutions that will also pollute the RF networks around you. So it's important also to consider those systems as you create your design. Why am I talking about interference? Is because the performance of the network that you will deploy will be highly dependent on the quality of the network that you have. What I'm showing on the left here is basically a table that showed the relation between the SNIR and the data rate. So the SNIR stands for signal to noise ratio. So what it means is basically the ratio between the useful signal and the interference that you have around you. So the stronger your useful signal is compared to the interference around you, the higher the throughput that you will get on LTE. So the more throughput you have, the more users you will be also able to support in your network. So this is the reason why considering the interference is very key to ensure that you're going to meet your KPIs. Another aspect that is important also to consider is if you're working on a high-rise building, you might have a different impact of the macro network as you go up in the building. The more you go up, the more direct line of sight that you will have with macro network towers around the building. And so the level of interference that you have will go up, and the consequence of that will be that your throughput and capacity will degrade as you go up in the building. You might have additional drop calls, and in some cases as well, you might be stealing capacity from the macro network, which is not a thing that you want in your design. So what you see on this diagram is basically a design done on different floors. So the signal strain that you have for the in-building system is equivalent on all the floors. But as you go up in the building, we have about 1 dB extra of noise as you go up in the building. So you can start with floor 5 where you have a very, very good network, allowing user to have data rate of up to 58 megabit per second. But as you reach floor 25, with the same network but more interference, you degrade your signal quality, and now an important portion of your floor has degraded signal that could go down to 1.1 megabit per second. So that shows that it's very important to consider noise level as you do your design, and do that for all the floors that you have. So how do you take into account the macro network? So at iBwave, in our software iBwave design, we support 3 ways to support the macro network interference. The first way would be to use a given interference value. So this method is fairly simple. You just need to read the signal level around the building as you go on site. You measure it once with your cell phone, and then you basically estimate that you're going to have the same level of interference all around the building. So this is used for a quick evaluation of the interference and is fairly low cost. Obviously, there's more precise way of modeling the macro network. The ideal solution would be to measure the interference from the macro, you doing a site walk inside the building. So you can use any collection tool vendor application, and then just go and measure the signal level for the bands that you are deploying inside the venue. So this is obviously the most accurate method. You're going to have a good reading of the interference at any location. And for best accuracy, we recommend to do that for at least every 3 floors for the reasons that I mentioned earlier in the call. And lastly, there might be some cases where the measuring the signal on site is not possible, especially for new constructions. So another way that might be that may give you pretty good modeling of the macro network would be to import prediction from other prediction tools. So so the macro network and design tools have functions to export their prediction around a specific area. So this information can be imported into iBwave design to model the macro network interference. The software will then interpolate the signal throughout the building and will use that to create interference map. So this solution is lower cost than measuring it, but might be your best option in some cases. So what about small cells? So small cells, it has many advantages. It's relatively cheap to deploy as compared to traditional DAS, passive or active solutions. And they allow you to add capacity in a targeted location inside your building. And most of them now today have self-optimization capabilities that allow to basically configure themselves with power and manage the interference between them and with the macro network. But as you create your design for small cells, there's additional consideration to take into account. The most important thing is traditional small cells will act as independent cells inside the building, and each of them will interfere to each other. So for that reason, as you do your design, you need to consider some good isolation between small cells. Ideally, you would have some physical frontier between the location of these small cells to limit the interference that you have between them. And it's important also to control the end of zones of your on your floor plan and make sure that the phones are transitioned at the right location. If you look at the design on the right, this design would have to be improved. What you have is basically 3 small cells, and as you see close to the small cells, you have very good data rate. But as you go in the middle of those 3, this is where you have the highest interference between those 3 small cells. So in this case, the designer has created a zone of interference directly in the lobby area where you want very good coverage for the people waiting and want to access their email and internet on their phone or tablet. So preferably you would have those zones of end-off where you have low attendance of users to limit the impact of those zones. So in conclusion, as you plan for your small cells design, it's very important to understand the user requirements and behavior to ensure that the quality of experience after the deployment will meet their needs. A precise modeling of the macro network is also very important. It might impact greatly the level of interference, and if you don't do it upfront during the design, you might run into cost overrun in the later phase of the project. And lastly, the inter-cell interference for traditional small cells is another aspect to consider and to plan appropriately to meet your KPIs of throughput and capacity. So from here, I will pass the control to Josh from Airvana to present their case study.
Thank you, Marc-Antoine. So now I will talk about how we at Airvana use the iBwave tools in relation to our products and also our customer deployments. And I'll use a case study to illustrate this. So, okay. It looks like I have controls. Sorry about that. So first, a few words about Airvana. We are a 15-year-old company. We've always been focused on mobile broadband. Originally, that meant 3G macro base stations. Now we're focused on 4G and small cells. Last year we announced a Cloud RAN or C-RAN small cell product called OneCell, and that's the product that will be featured in the case study that I will present. Last month we were acquired by CommScope. CommScope is a leader in distributed antenna systems, or DAS, so together we offer a very broad in-building wireless portfolio. For the purpose of this discussion, I'm going to be focusing on large venues, and by this I mean large public or quasi-public spaces, such as stadiums and coliseums, airports and railway stations, shopping malls, resorts and hotels and convention centers. And what do all these places have in common? First of all, they have a lot of people, and people tend to be using their wireless devices in these venues. So there's intensive wireless activity. So it's very important for operators to serve these kind of environments well, but these are also some of the most challenging environments to serve, in part because they are often, though not always, indoors and therefore far from a good macro signal, and also just the intensity and concentration of use can be very difficult for any type of system to support. Within small cells, there are now really two major architectures for supporting these indoor spaces, and I will talk about them briefly. And by the way, Airvana makes both of these kinds of products. So the first is what I would call a traditional small cell or standalone small cell. These were originally developed for residences and small offices. In the case of the standalone small cell, each access point forms its own cell. Now, these can be used in larger venues by deploying an array of access points. However, since each one is its own cell, this type of deployment can create cell borders, which in turn creates interference and the need for handovers between the individual cells. The standalone small cells typically support a single operator, and the capacity is static. And what I mean by static capacity is that each small cell, each access point will have its own capacity, say 32 or 64 users, which works fine as long as the users are then distributed evenly throughout the facility. But as we know, in many of these kinds of facilities, that's not the case. So for example, in a sporting event, you have halftime or some kind of break, and then everybody goes to the concessions or the bathrooms or things like that. So people move about. And if the capacity is tied to the access points, what that means is you might have a situation where there are more people around cell A than cell A can service, and meanwhile cell C has idle capacity. Now, that brings us to the alternative architecture, which is Cloud RAN or C-RAN small cells. In this case, we have multiple radio points connected to a single centralized baseband controller. And the LTE scheduling takes place in the baseband controller. So this creates a single cell across multiple radio points. Because of this, there are no borders or handovers. It also is a multi-operator architecture. Now, one of the things they both have in common is that they use Ethernet for distribution, and this reduces the cost. So you can think of the C-RAN small cells as providing many of the benefits of a distributed antenna system, but at cost points that are more similar to standalone small cells or managed Wi-Fi systems. Now, as I mentioned, Airvana makes both types of products, but for large spaces with a high number of access points, we consider C-RAN to be the more appropriate architecture. Having said that, C-RAN is a relatively new architecture. So one of the things we have done is to work very closely with iBwave to ensure that we can model this architecture accurately in real deployments. Now, as I mentioned, the C-RAN architecture is really designed in large part for superior customer experience. As I mentioned on the last slide, it creates a single cell which eliminates border interference and handovers, but there are other aspects to improve performance as well. So there is coordination between the radio points that allows for joint downlink transmission and uplink combining. And the net result of these kind of techniques is a higher data rate, as we'll see in some of the modeling. Also, by centralizing the baseband processing, we also centralize the capacity. So this system doesn't particularly care where the users are, as long as they're in the larger cloud served by the same baseband controller, they can be served by that controller. So that you don't have this issue of people moving about and having situations where you cannot serve the capacity because of the distribution of people. Also, and finally, Mark mentioned the importance of managing macro interference. And as it happens, you can manage macro interference mitigation much more simply with a C-RAN architecture, mainly because you are creating a single cell. So many of the methods for managing macro interference have to do with coordination between the macro network and the small cells. In the case of standalone small cells, this is very complex because you might have 20 or 40 individual standalone small cells with which the macro needs to coordinate, and this becomes practically impossible. But with a C-RAN system, you really only have one cell, or at worst a very much smaller number of cells to coordinate with, so you can apply some of the mitigation techniques more effectively. Next, I will talk about an actual deployment, and in this case, this was with a U.S. regional operator called Nex-Tech Wireless. The user was a university called Fort Hays State University, and in particular their Coliseum, which you see pictured here. It's a typical university Coliseum. It seats up to 7,600 people, which is not huge for a Coliseum or stadium, but it's the equivalent in terms of user numbers to a 30 or 40-story office building. So it really is a quite large and demanding environment, especially when you consider that all of these people are packed into a relatively concentrated space. Now, in the next few slides, I will go through the system design, how we modeled the performance using iBwave, some actual performance metrics that we have collected during live events, and finally offer some conclusions. Here's a picture of the floor plan of the Coliseum. As you can see, there are 3 levels in the Coliseum that needed to be covered, plus an adjacent hall with office space in it. Just touching on some of the things that Mark mentioned, we had the issue of ingress and egress, and as you can see, the small dots are the radio points. They're a little hard to see in these diagrams, but we made sure to have some near the ingress and egress points so that we would efficiently hand in from the macro and hand back out to the macro when people left the facility. In terms of macro interference, we did measure this on site. As it turned out, it wasn't too much of an issue here just because of the nature of the building. It's a very heavy construction building with concrete and steel exterior, so the macro signals did not leak too much into this building, and likewise, our signals did not leak out very much. In this design, we used two overlaid carriers, or I should say Nex-Tech Wireless used two overlaid carriers, a 700 and a 1900 megahertz frequencies, to be sure that there was adequate capacity for all of the users in the stadium. And in this design, each of the frequencies is operating across the entire space. So if you come in, whether you are picked up on the 700 or the 1900, you would never experience a handover or a cell border as you move about through the Coliseum. You can stay on that frequency the whole time and be serviced by it. The baseband controller that I mentioned, you can see on the second floor on the right-hand side of it, and it's attached to Ethernet switches, which not only use the Ethernet IP over Ethernet networking as a distribution method, but also use power over Ethernet to provide power to the radio points. And that way, there was no need to run separate electrical wiring to the radio point locations, which in this case was a huge benefit because you know, some of the radio points were on the ceiling of the Coliseum, which is very high up. So you don't want to run more to those locations than you absolutely have to. The reason there are two radio points in each location is for the two bands. So we had a set running at 700 and a set running at 1900. And for backhaul, we had a 100 megabit per second backhaul link. So next I will talk about how we use iBwave to model the performance. And as I mentioned before, we have both standalone small cells and C-RAN products. So we wanted to model both of them. And this next couple of slides shows the comparison. So the first comparison at the top of this slide is for signal strength measured through RSRP. And in this case, the signal strength is a little bit different, but not meaningfully so. So the differences would never be observed by a user. But if you look at signal quality on the lower half, as measured by SINR, this is a very different picture. So here on the left with the standalone small cells, what you see is a pretty good signal right next to the access points. But as soon as you move even just a few tens of feet away, the signal quality drops considerably. And that kind of irregular blue cross that you see across the center of the Coliseum is effectively a dead zone. And that's because of the cell borders that are created in those locations. By contrast, the C-RAN architecture provides an incredibly uniform signal quality across the entire space. Not only is it uniform, but it's at very high 20s of SINR. So it's uniform and it's very good. And in part, this is because the radio points do not interfere with each other, but in addition to this, they actually reinforce each other. So if you think about it, a mobile phone at the very center of this diagram would see equal signal strength from both systems, but it would see a much better signal quality from the C-RAN, the OneCell C-RAN system, because it's actually seeing signals from all four of the radio points that are in the four corners of the location. Now, SINR is a useful measurement for people like the people on this call, I imagine. But for a facility owner or an end user, they don't understand SINR, but they do understand data rates. And so one of the things we've taken advantage of within the iBwave toolset is the optimization module, which offers a data rate modeling. it's called maximum achievable data rate, and it interpolates this from the signal quality. So here in this slide, you see the same comparison and the table of data rates that are achievable. And what you can see, once again, is that the standalone small cells offer a pretty good data rate right next to the access point. But as you move away, the data rate drops considerably. Whereas with the C-RAN solution, you get the maximum achievable data rate pretty much uniformly throughout the space. And this is the maximum rate, which is just about 60 megabits per second on a 10 megahertz channel. So it's very good. Now, so far, this is very promising, but this is modeling. It's a prediction. So we also obviously needed to see how the real system performed once in place. And for that, we enlisted the help of our friend Sparky. Sparky is a robot that Airvana has developed just for this kind of purpose. It performs essentially what you would call walk-around testing, and it takes measurements at very frequent intervals throughout an area and moves about in a more or less random pattern to do this. And the benefit of Sparky, unlike using engineers to do this, is that Sparky never gets bored, so we can just set him going, and he'll walk around for hours and do this kind of testing. So what I want to show you in the next couple of slides is how the results of this testing compared to the modeling that we had done with iBwave. So in the first case, we'll show the SINR comparison. On the left, you have the iBwave model, which we saw a few slides ago. On the right, what you see, if you look closely, is the path that the robot took. And it's a little hard to compare this visually because the robot is only recording measurements for actual places it had been. So it can't show you a big area the way that iBwave can. But if you can look closely, what you'll see is that the color that represents the signal quality is pretty much identical to what the iBwave tool predicted it would be. And what we also have showing the data from the robot in a different way at the bottom is a cumulative distribution, probability distribution of signal strength across all of the areas that the robot measured. And what you can see there is that at any given point throughout this floor, there's a nearly 100% probability that the user will receive a signal quality of the high 20s of dB. And only when you get up to 30 and above do you see this drop off. We did the same thing for the data rates, and you see the same kind of result, that the robot testing showed almost identical results to the iBwave modeling. So this gave us a lot of confidence in the iBwave design, seeing this very tight similarity of measurement. Now, the robot measurements are real in the sense that they're measuring the actual signals in the real physical venue with the actual system, but they are taken during an idle period, and this is for practical purposes. You can't have the robot walking around and bumping into basketball players or graduating seniors. It really is something you can only do during an idle period. So we also felt we needed to model the system or test the system under load during a live event. So for this, we picked a university graduation ceremony in which the Coliseum was pretty much full. And as you can imagine, during a graduation ceremony, there's a lot of smartphone use. People are posting to Facebook. They're taking pictures and sending messages to people who are not there. Maybe they're even bored, and so they're just playing games or checking Facebook or whatever they're doing. But I can tell you, because we had people at the ceremony, that there was lot of mobile usage going on there. What we had, Nex-Tech Wireless also had engineers in place at the ceremony throughout the duration of the ceremony at different places doing speed tests. And what we measured was peak speeds of 66 megabits per second, and these were achieved very consistently throughout the area and throughout the time. This is on a 10 megahertz channel, where the maximum theoretical LTE throughput would be 75 megabits per second. So we are, in this case, right up near the theoretical maximum. So it's very good. We also have measurements from the system itself. The downlink channel quality was an average of 13.5, and that is against a maximum achievable of 15. So it's very good. And the uplink SINR that was observed by the system averaged over 26 dB, which again is very good. Now, so far we've talked about signal quality and data rate measurements, but obviously there are other kinds of KPIs that impact the user experience, things like call or connection setup rates, drop rates, and handover to the macro network. And the bottom line here is that the excellent signal quality also provides for these kind of KPIs to perform extremely well also. So you can see we had a 99.7% connection setup success rate, very low call drop rate, and we encountered no errors handing over between the small cell system and the macro network. So that's the case study. Let me just offer some concluding remarks. Up until this point, small cells have not been considered an appropriate solution for large venues. In fact, it's almost been considered an oxymoron. So we feel that this is a major accomplishment to have performance like this in a crowded Coliseum, and it really proves the power of the C-RAN small cell architecture. However, it's still critical for us and for our operator customers to have tools to make sure that we get the design right so that we can be confident about the outcome and the results, and that the design delivers what the technology is capable of and what operators and end users expect. So for us, using the iBwave tools and working with iBwave has been a critical part of this process and will continue to be going forward. So I hope this gives you a flavor of how our solutions are used and how iBwave is helping us. And now I believe we have time for some questions.
Thank you, Josh. I hope all of you were able to take some new knowledge today. Now we will get to some of the many questions that were asked during registration and throughout this webinar. If you have any additional questions, you can still type them into the questions box on the GoToWebinar control panel. We will answer as many as we can, and then the rest we will get to after the webinar. So the first question I have is, can you highlight key differences in planning small cells, indoor DAS, active DAS, and C-RAN solutions?
Okay, I can take that one. Thank you, Amna. So there's similarity in the design for all these solutions. Obviously, designing your solution, taking into account the macro network and planning for throughput capacity, all of that is important for all these solutions. In the case of passive DAS or active DAS, additional consideration needs to be taken into account for the passive portion of your network. So you're going to have signal go over coax equipment, which will degrade the signal. So it's important that to have a tool that will make those calculations and give you the adequate output power at each antenna to have the right level of coverage inside your venue. In the case of small cells and C-RAN solution, you might have also to consider the backhaul capacity. If you have to connect those equipment to an existing Ethernet network, you have to make sure that your network will have enough throughput at any point in the network to support the throughput generated by each individual cell, and also you have to consider that those are connected to the network via the internet connection. So again, you need to calculate and plan the backhaul capacity that you will have to your through the internet to your network.
Thank you, Mark. The second question I have is, if OneCell creates just a single cell, how can it deliver enough capacity for stadiums and other large venues? And the second part of this question is, how does OneCell support multiple operators?
Okay, thanks, Amna. I will take that. So these are great questions. First of all, let me address the single cell question. So we have a couple of ways that we increase capacity beyond what you would expect from a single cell. The first and most obvious one is that in architectures that have multiple cells, you may not really get multiple cells worth of capacity simply because of the interference. So in those modeling diagrams we saw, in those cases they were 4 cells, but as you can imagine, they were not getting 4 cells worth of capacity. Whereas with the C-RAN architecture, because there's no interference between the access points, you really do get the full capacity of the cell. Now, beyond this, we have a technique that we call smart reuse that dynamically allocates additional capacity within the system. And I'll try to give a simple explanation of this. Imagine in a large area, you have 2 users who are separated by 20 or 50 meters distance. Chances are they are being covered by different radio points, and that their mobile signals would never interfere with each other. Our system knows the location of the users and their relative signal strength and what radio points they're being served from, and this allows us to allocate the same LTE resource blocks to different users, and therefore we multiply the capacity of a single physical cell to multiple virtual cells through this technique. And obviously it depends on the space and topology and the location of users, but what we have seen is the ability to multiply capacity by 4 to 8 times using this technique. The final thing I will mention is that, just to pick up on what Mark mentioned a moment ago, is the backhaul. So if you have, say, 32 small cells, standalone small cells, each with, say, 20 megahertz of capacity, and then that becomes, I can't do the math right now, but many hundreds of megabits. And chances are you're not going to have that backhaul capacity, or you might not want to have that much backhaul capacity. So when you're looking at capacity, you have to look at the whole end-to-end system, not just the radio access network, but also the backhaul.
Thank you, Mark. So another question I have is, are Airvana C-RAN components already in iBwave?
Okay, so I can take that one. So yes, the OneCell is modeled in iBwave, so it can be downloaded from the online iBwave catalog. Those have been modeled already a few months ago in conjunction with the team at Airvana to make sure that we are modeling adequately this type of solution. So yes, they are supported in iBwave.
Thank you, Mark. There's another question. What is the maximum level of interference from macro you think it's still acceptable for installation of small cells?
Is that a question that you want to take, Josh?
I will take a shot at it, but then interested in your comments. Yeah, so I mean, it really depends on your objectives for the system and the kind of service you're trying to offer people. For voice only, you can have a reasonable amount of interference because you need a relatively low bandwidth signal to carry the voice. But if you're really trying to offer data, high data performance, then you can't afford too much, and it's just measured by the SINR.
And maybe just to add to your answer, we've seen deployments like this where the macro network was very strong, and instead of trying to beat the macro network, and if the capacity on that macro is not so much an issue, in some cases we've seen deployments where the operator have decided to make use of the macro network coverage in some portion of the building, and then use small cells in the areas that provided less coverage. So this is kind of a hybrid deployments where you can leverage the macro network to provide some level of coverage also as part of your in-building system.
Thank you, Mark. So we'll just ask one more question. What is the difference between the C-RAN and a simple passive DAS connected to OneCell?
Okay, I'll take that one. Let me answer it in two ways just to make sure that I understand the question. First, I'll just talk about the difference between C-RAN and passive DAS. With C-RAN, with a passive DAS, you're basically using a macro-style base station and then extending the signal to different antennas. This typically uses analog signals over coaxial cable, and therefore you have issues with power loss as a function of the length of the cable. And so even though passive DAS is simpler than active DAS, you still have the challenge of calculating the signal, whereas with a C-RAN system, you have a digital communication. It's IP over Ethernet all the way to the radio point, so you don't have to worry about signal loss. Some other differences, I mentioned this smart reuse capability. There is no reuse with a passive DAS. It is a single cell or single cell per sector, and also some of the intelligence of things like uplink combining or is not really possible with DAS. Now, the other way I interpret this question is maybe it's talking about using OneCell as a signal source for a passive DAS, and that is certainly possible. The OneCell is effectively an eNote B, but if you use it this way, you are not getting a lot of the advantages of the C-RAN system, because essentially you're still distributing through the passive DAS methodology. So as a result, we haven't seen much interest in that particular solution. So I hope that answers the question.
Thank you, Mark. We actually just have one a little bit space for one last question. And that question is it possible to provide coverage and capacity to open stadiums with 75,000 seats or attendees?
The answer is absolutely yes. So the case study that we showed here was much smaller by a factor of 10 than what the user is asking about. But having said that, it only required a single OneCell system per frequency band. So you can absolutely have multiple OneCell systems throughout a stadium like the one that's being described. And also using the smart reuse capability, it actually has, in some ways, it creates fewer sectors than an equivalent DAS system.
Thank you, Josh.
And I should mention that we're currently working with operators on designs for such stadiums, although I can't name them at this stage.
Thank you, Josh. Unfortunately, we're out of time, so I would like to thank everyone who joined us and offer all your questions. To continue the conversation, I will start a thread on our LinkedIn group, the iBwave in-building community. If you're not a member yet, I encourage you to join us and take part in this discussion. You can also look forward to the recording and the slide deck from today's presentation, as well as the case study associated with today's webinar within the next few days. Once again, thank you for taking the time and have a great day. I will now disconnect the call.